the sum of digits function that we defined in the last lesson, here it is, seems to be so simple and natural that there's no other way to do it. But this intuition is actually completely wrong. There is a very different way to write some digits, which is actually a lot better. So in order to introduce this, let's first start with a simpler function, the factorial function, and then we'll get back to some digits. So let me now write the factorial function. Let me first write a specification, so a mathematical definition of factorial. So 0 factorial is equal to 1, and n factorial is equal to n times n minus 1 factorial when n is bigger than 0. So this is a mathematical definition of factorial. We can translate that into a program. Let me call it fact1 because it's our first version. So if n is equal to 0, then 1, else n times factorial 1 of n minus 1. And that's it. So our program follows very closely the mathematical definition, the specification. So let me feed this to the system now. Feed region, and let me now just show you how this works. Factorial 10 gives me 3,628,800. Fine, this is one way of doing it. But in fact, there is a completely different way, which we will see is much better. And this different way starts with what we call an invariant, so a formula that is true during the execution. And from this, we can derive a function. And we'll see that this will give us a quite different factorial. And then we'll see later that it's actually a much better one. So let me bring in a slide here. So the point is, we start by inventing a formula that splits the work we have to do into two parts. So here we have to calculate n factorial. So we have n factorial, and we split it into two parts. It's I factorial times a, okay, with the I and a. And we will start with I is equal to n, and a is equal to 1. So we don't really know the result yet. We still have a 1 here, and I is equal to n, so that the formula is true. N factorial equal n factorial times 1. Now the trick is that we decrease I and increase a, but at all times keeping the formula true. And finally, when we end up with I equals 0, then a is going to be the final result. So here's an example when n equals 4. We start by saying 4 factorial is equal to 4 factorial times 1. Now we will reduce the I. First we reduce it to 3. In order to keep the formula true, we have to multiply the a by 4. Then we reduce it to 2. In order to keep the formula true, we have to multiply the 4 by 3, and so on. Eventually we end up with 0 here, and 24. And 0 factorial, we know what it is. It's equal to 1. So we have finally the result, which is 24. Okay? So this is another approach, and this actually gives us a different program. Let me put it here. Let me call this principle of communicating vases. So in this principle, we start with n factorial is equal to I factorial times a. Now the trick is we want to decrease I by 1 each step and increase a. So this gives us I times I minus 1 factorial times a. And now, in fact, in order to keep the formula true, we need a new value of I. So we can say this is I minus 1 factorial times I times a. So we have an I prime, a new value of I, which is equal to I minus 1, and an a prime, a new value of a, which is I times a. So there are these two values, I and a, together. So our new function now will have two arguments, I and a. So let me write it. Fact2, I and a. Now we also have an if statement. Remember, we decrease I. So when I gets equal to 0, the result is a. Otherwise, we have our I prime and our a prime here, the new value of I, the new value of a. So the I prime is I minus 1, and the a prime is I times a. And there we get our recursive call. So this is a new definition. I feed it to the system. Let me check it. So we have to start with the initial value of I and the initial value of a. So if we want to do 10 factorial, we have 10, and the initial value of a is 1. Calculate this, and it gives us the same result.